With a diameter of almost 140,000 kilometers, Jupiter, the king of our planetary system, is so large that the Earth would theoretically fit into it over 1,300 times. In the same breath, this enormous gas giant is about 2.5 times more massive than all the other 7 planets in the solar system combined. But did you know that this planetary colossus is a real Speedy Gonzales despite all of its size? In fact, Jupiter only needs a little less than 10 hours to rotate around its own axis, making it the fastest rotating planet in our home world. But aside from its captivating beauty, Jupiter is also the scene of colossal storms and deadly radiation. What secrets lie hidden beneath its dense bands of clouds? What do we know about the Great Red Spot, which is larger than Earth and whips across the planet's outer layers at a crazy speed of up to 680 kilometers per hour? And above all, how could our own planet never have come into existence if Jupiter hadn't been rampaging through the solar system like a crazed berserker? In the beginning was Jupiter, or at least that applies to the formation history of our planetary system. A few years ago, researchers at the University of Munster were the first to successfully determine the true age of the imposing gas giant. However, since the celestial body has no solid surface and therefore cannot provide rock samples, the experts had to take a small detour in their age determination and draw their conclusions from meteorites. The bottom line, however, was the realization that Jupiter had grown to 20 Earth masses in less than 1,000,000 years after the formation of the solar system, and that its development was fully completed after another 3 million years. By way of comparison, Earth, whose mass is about 318 times smaller than that of Jupiter, took a whopping 100 million years to reach its planetary completion. While the mighty celestial body is not only the largest but also the oldest planet in our home system, it was once formed from the dust and gases left over from the formation of the Sunday the 4th of June billion years ago. This supply of material is also reflected in the composition of Jupiter. Just like the Sun, the gas giant is mainly composed of hydrogen and helium, which incidentally also explains its comparatively low mean density of 1,330 kilograms per cubic meter. But although the Sun and Jupiter are proverbially cut from the same cloth, there is now an average distance of 778 million kilometers between them. In detail, the double XXL planet orbits beyond the asteroid belt, between the orbits of Mars and Saturn. As a result of this constellation, it takes just under 12 years to orbit our central star. Well, strictly speaking, that's not entirely correct either. Because if we are very meticulous about the facts, Jupiter does not orbit the Sun at all. What is meant by that? To understand this, we have to take a small detour into the world of barycenters. The barycenter describes nothing more than the center of mass that planets and stars orbit around together. This is usually closest to the object with the greatest mass. Since the mass of the Sun is 333,000 times greater than that of the Earth, the barycenter, in this case, is very close to the center of our mother star. However, as already mentioned, Jupiter is significantly heavier than our home planet, and because of this, we find the center of gravity of Jupiter and the Sun not at the center of our home star, but just outside the surface of the Sun. Jupiter goes astray. As a general rule, the greater the mass of a body, the stronger its gravitational pull on another body. Since Jupiter has a lot of mass, about 318 Earth masses, its gravitational force influences the structure of the solar system in a variety of ways. This starts right on its doorstep. We now know of 95 moons that are bound to Jupiter's gravitational grasp, but that's not all. The subglacial ocean of Jupiter's moon Europa is even suspected of harboring extraterrestrial life forms. However, further investigations will have to show to what extent this exciting theory ultimately matches reality. So far, the gas giant has been the focus of probe-based research missions and flybys 7 times. In fact, the NASA probe Juno is still dedicated to the task of exploring the Jupiter system in detail. The scientific relief is already on its way. The ESA probe JUICE set course for Jupiter on April 14, 2023, and is scheduled to reach the gas giant in July 2031. So far, so mission-focused, but if we now turn back to the literal attraction of the gas giant, we see that its gravity exceeds that of Earth by more than 2.5 times. Jupiter consequently acts as a kind of natural protective shield. In other words, due to its considerable mass and large gravitational field, it deflects comets and asteroids that could otherwise hit Earth. In other systems, however, proximity to such massive planets is not always an advantage. One research study concluded that the attraction of planetary giants not only deflects dangers but also sometimes catapults smaller planets out of the habitable zone. And speaking of being catapulted out, Jupiter also has a history as a cosmic wrecking ball. Experts now assume that the gas giant was originally formed 4 times further away from the Sun than its present orbit suggests. In addition, there have long been indications that Jupiter even temporarily migrated into the inner solar system. In doing so, it caused unparalleled chaos, but on the other hand, it also enabled the Earth to form. The corresponding simulation by scientists showed that the gravitational pull of Jupiter's migration carried enormous amounts of debris and planetary building blocks with it. We are talking about planetesimals up to 1,000 kilometers in size and a total of 10 to 20 Earth masses of material. But it's in the nature of things that this planetary walk of a somewhat different kind did not remain without consequences. It actually triggered a veritable chain reaction of asteroid collisions, which destroyed larger planetary nuclei and caused a large part of the debris to plunge into the Sun. The once very dense accretion disk near the Sun was thus severely thinned out in the affected region, and the situation only calmed down when Saturn formed further out and Jupiter reversed its migration direction. Due to this, Jupiter's passage swept the interior of the early solar system empty, which paved the way for the second wave of the formation of small gas and rocky planets. Our Earth was also among them. But this scenario also provides an explanation for the anomaly of the solar system. In hardly any other known system do the innermost planets start as far out and have as little gas as ours. Instead, most extrasolar gas giants or super-Earths orbit their host stars very closely and quickly, and they often take only a few days or months to complete an orbit. Why the Great Red Spot trembles? Let's detach ourselves from the turbulent history of Jupiter and instead take a closer look at its optical appearance. We immediately notice the unusual subdivision of the planet, and what at first glance may look like a fashionable striped pattern is actually a series of almost parallel bands of clouds that can be seen even through small telescopes. These bands range in color from white to blue, and experts distinguish between the lighter zones and the darker belts. While the zones are significantly cooler and denser than their counterparts and also contain rising gases, their lighter color is likely due to ammonia ice. However, why the belts appear significantly darker is not yet fully understood. In principle, researchers assume that phosphorus, sulfur, and perhaps even hydrocarbons are present in them. Surprisingly, experts have observed a periodic color change in the conspicuous bands every 4 to 5 years, which may be related to cyclic oscillations of Jupiter's magnetic dynamo. Furthermore, the zones and belts are bounded by so-called jets, which race over the outer planetary layers at wind speeds of about 300 km per hour compared to the speed of the Great Red Spot. However, that's nothing. The largest cyclone in the entire solar system actually moves at speeds of up to 680 km per hour. However, it's not known which chemical elements are responsible for the red coloration that gives it its name. What is known is that the gigantic anticyclone is currently about 1.5 times the diameter of the Earth and has been raging on Jupiter since at least 1830. By comparison, the wind vortices in the Earth's atmosphere usually belong to the past after only a few weeks. Despite its considerable age, the Great Red Spot has now shrunk considerably. While its length was still estimated at 40,000 kilometers in the 1880s, it is now only 16,500 kilometers. Suspects that this is due to interactions with other small storms. Could its own loss of size also be the reason why this monstrous structure is literally trembling? Well, probably not. New observations with the Hubble Space Telescope have recently shown that the Jupiter storm changes its appearance several times during its 90-day migration from east to west and back again. The Great Red Spot alternately narrows and widens as it drifts faster and slower. These oscillations also go hand in hand with periodic fluctuations in the size and brightness of the storm's eye, which, however, are inversely proportional to the drift rate. In fact, the Great Red Spot and its eye are at their largest and brightest when the cyclone is drifting at its slowest. The characteristic change a little from day to day, and in time-lapse, it looks as if the Great Red Spot is shaking like a leaf. But why is that? Well, we don't know yet. After all, This is the first time that such an oscillation has been observed in a Jovian cyclone. The scientists have yet to provide the corresponding hydrodynamic explanations, but the assumption is that the interactions with the violent shear winds of the storm bands north and south of the Great Red Spot are responsible. What will happen next? Given the past reductions in size, how likely is it that the monstrous structure will one day completely disappear from the Jupiter scene? Well, this is precisely the question that the experts are currently addressing. They now want to find out in detail whether there is a lower size limit beyond which such a long-lived cyclone becomes unstable. How many clicks will make the thumb and subscribe buttons unstable? We hope you enjoy participating in our scientific Pacific experiment, while never missing a new video from us again. We'll see you soon.